Now in the second part of this problem, let's look at part B. Suppose that the electron in figure is replaced by a proton with the same initial speed v0. Would the proton hit one of the plates? If not, what would be the magnitude and direction of its vertical displacement as it exits the region between the plates? Part C, compare the paths traveled by the electron and the proton and explain the differences. And part D, discuss whether it's reasonable to ignore the effects of gravity for each particle. Okay, now the free body diagram for the proton shows that because the electric field is pointing down and this is a positive charge, this is a negatively charged plate, so the proton is attracted. So it has a force Q times the electric field pointing down, and the weight is also pointing down. The electrical force Fe is the proton charge plus E times the electric field E, which is equal to 5.82 times 10 to minus 17 newtons. It's the force, the same force we have calculated in part A. Now the gravitational force the proton feels is mass of the proton multiplied by gravitational acceleration. Mass of the proton is 1.67 10 to minus 27 kilograms times 9.8 meters per second square. We find 1.64 times 10 to minus 26 newtons. Now you can see 10 to minus 17 is much greater than 10 to minus 26. So we still have the electrical force being much greater than the gravitational force. So therefore that's the only force we should consider. So this is the trajectory of the proton that we envision. You can see here it's attracted to the negatively charged plate. Now whether it will make it to this plate or whether it will be a small displacement, we have to find. Now the distance it travels inside this electric field, delta x, is the same initial speed v0 times delta t, and the distance traveled is 2h. So the time spent in the electric field is identical. It's going to be equal to 2h divided by v0. The displacement on the y-axis for the proton, delta y proton, will be equal to 1 over 2 the constant acceleration on the y-axis, delta t squared, and once again the constant acceleration on the y-axis is the electric force E times the electric field divided by mass of the proton, since I'm neglecting the gravitational force. Now if I look at the displacement of the proton, delta yp, this is 1 over 2 acceleration E electric field divided by mass of the proton times the time spent in the electric field squared, delta t squared. And if I compare this with the displacement of the electron, delta y electron, which is 1 over 2, the same force, E, electric field E, divided by this time the mass of the electron for the acceleration, times delta t squared. You can see that their accelerations are quite different. So the ratio of the displacements, delta y proton divided by delta y electron, is actually the ratio of the masses, mass of the electron divided by mass of the proton. Now, since we have mass of the electron 9.11 10 to minus 31 kilogram, much less than mass of the proton 1.67 10 to minus 27 kilograms, we have this much less than mp. Delta yp, the distance traveled on the y-axis for the proton is me divided by mp, so it will be much less than the distance traveled on the y-axis for the electron. So that means the proton does not hit any of the plates. So that's the conclusion. And what is the distance traveled by the proton? it is the distance traveled by the electron, which is h over 2, multiplied by mass of the electron divided by mass of the proton. So this is going to be the answer for the displacement of the proton. Now, if we substitute the numbers, delta yp, we will find 1 centimeter divided by 2, that's the displacement of the electron, multiplied by the ratio of the electron mass, 9.11 10 to minus 31 kilograms, to proton mass, 1.67 10 to minus 27 kilograms. That is 2.73 times 10 to minus 6 meters. So we find that the displacement of the proton is minus 2.73 times 10 to minus 6 meters in j hat, in minus j hat direction. In meters, it's actually, we can write explicitly as downward direction. All right, so this is the answer to part B of the question. Now in part C, we were asked to compare the path traveled by the electron and the proton. The electron displacement was in the upward direction. The proton displacement is in the downward direction. And the electric force, the electron and the proton field are the same, but because the masses are so different, mass of the electron is much less than the mass of the proton, the acceleration it causes will be different. The acceleration it will cause on the electron will be greater than that of the proton, which will result in a displacement of the proton much less than that of the electron. So the electron displacement is in the upward direction. The proton displacement is in the downward direction. The electrical force magnitude Q times E is the same, since the magnitude of this force is E times electric field and the magnitude of the charge is E for both particles. But since mass of the proton is much greater than mass of the electron, we see that the displacement of the proton is much less than the displacement of the electron on the y-axis. In part D, we were asked to compare the gravitational force for each particle. In both cases, we have the same effect. The electrical force is the same. It is 5.82 times 10 to minus 17 newtons. I calculated the gravitational force for the electron. It is of the order, let's see, 10 to minus 30 newtons, or 10 to minus 29, because it's 8.9 10 to minus 30. And for the proton, it is of the order 10 to minus 26 newtons. So they're still much smaller than the electrical force. So the one of the electron is 8.90 10 to minus 30 newtons. The weight of the proton, the gravitational force on the proton is the weight of the proton 1.64 10 to minus 26 newtons. Therefore, gravitational force is negligibly small for both cases. So this is our conclusion in this discussion. So we have repeated this exercise for the proton. In the case of the proton, we see that the force is pointing down, so QE is pointing down, the weight is pointing down, but the weight calculation shows much smaller value than the electrical force, so we can neglect it. So this can be neglected in this discussion, just as we did in the electron. So The displacement on the x-axis is v0 times delta t. It is projected with the same initial speed v0, remember. So this has an initial speed v0. So the time spent in the electric field is 2h over v0. The width of the plates is 2h. The displacement on the y-axis is 1/2 a y delta t squared constant acceleration motion. The value of acceleration is quite different from that of the electron because of the larger mass of the proton. So the acceleration of the proton will be less than that of the electron. And this results in a displacement when I take the ratio of the displacements of the proton and electron. That of the proton is much less than that of the electron, and it is 2.73 10 to minus 6 j hat in minus j hat direction measured in meters. So it's h over 2 me over mp. The electron displacement is in the upward direction. That's what we found in part A. The proton displacement is in the downward direction. The magnitude of the displacement is a lot less for that of the proton because of the much greater mass of the proton compared to the electron, even though we have the same force in effect. And looking at the value of gravitational force for the electron, it is 10 to minus 29 newtons, of the order of 10 to minus 29 newtons. The proton is of the order of 10 to minus 26 newtons, but the electrical force is of the order of 10 to minus 16 newtons. 5.8 10 to minus 17 newtons. So it is much greater than the gravitational force. So it is reasonable to assume that gravitational force is negligible in this calculation.